Hello everyone, this is the video demonstration of our course project. Our project is exploring image classification and facial recognition techniques. Here we'll be exploring different feature recognition techniques like local binary pattern, histogram of oriented gradients, convolutional neural networks, and this is our team. That's me. And let's look at the problem statement we have here. This is the problem statement. So it states that identifying a face image by classifying into one of the key classes, extracting LBP, HoG, and CNN features using the code provided, and comparing different techniques. Here is a dataset in Kaggle. We'll look at briefly at the different techniques for feature recognition, like local binary pattern. So what it says is it looks at the center pixel, and if the outside neighboring pixels are bigger than it, then it will assign one. Otherwise, it will assign zero. So you can see five is greater than one, so one. Sorry, four. So it's one, one zero, one zero zero one one. According to the number of number present here, it assigns zero or one. Converting will convert that binary number to a decimal number. That will be 211. So decimal number ranges between 0 to 255. So all the will assign such decimal values to all the pixels present in the image, and will plot the like draw the image. So you can see example of the image here. This is a LBP image using the function we have created. And now let's look at histogram of oriented gradients. So what it basically does is it plots a histogram of by calculating the gradient magnitude and angles. How we calculate the magnitude is we calculate the gradient in the horizontal direction and the vertical direction, and we square add the square root of like add the square of the horizontal gradient and the vertical gradient, and take a square root of that, and that is the magnitude. And for the angle, we do arc inverse, tan inverse of gy by gx, that is vertical by horizontal. And now we have the magnitude for each pixel and the angle for each pixel, and we draw the image. For an example of the image can be seen here. These are the different gradients, and we have the angle here, like so suppose 45 degree or anything like that. And for convolutional neural networks, we have different kind of kernels. For you can see this is the Gabor filter kernel. This is the horizontal edges kernel. The features are here are mostly horizontal, and here these are mostly vertical. This is a different kernel. You can see example. There are different convolution layers, pooling layers, and convolution, and many such thing which are finally extract the feature. We will go into detail in the code section of this the video. Now let's proceed to the code. Uh, Here, this is the import section. This is the fetching and analyzing data section, and let's go down. This is the implementing different feature from extraction techniques. This is that section. This is using LBP. This is HoG. Wait a minute. That's CNN. And now we have implemented the different classification techniques with LBP, HoG, and CNN, and the results with that. And let's go to the import section. Here we have done the necessary imports for our project, like NumPy, Pandas, Matplotlib, CV2 Math, and all those required. Here we have faced the data. The dataset is quite large, so we have put some restrictions on that, like minimum 70 images per face and so on. So for X, we have extracted the data images, and for Y, that is the target, that is 102. Sorry, 1 2 3 4 5 6 7. The different levels. You can see the number of images are 1288 out of 34 or 34,000 or so images, and each image size is 50 by 37. You can see 50 by 37, and the number of unique classes are seven. The names for different people are given here. This is a sample. These are some sample images from the dataset with the labels, labels and target names written above. These are the distribution of classes in the dataset. The maximum number of images are for George W. Bush, and there are minimum 70 or 74 images for each person. The shape of each image is 50 by 37, and here is a sample of how what each image data looks like. It's between 0 to 1. Each value is between 0 to 1. That is normalized, and this is the example image of that. We can actually reshape the data into a single feature of 1850. Uh, that is 1 cross 1850. That 1850 is basically 15 to 37. Uh, an example of that is given here. Now we implement the different feature extraction techniques like LBP and all that. LBP, the feature extraction technique for LBP is done here. We have done that from scratch, and this is the original image. After using this function to extract the image extracted can be seen here. This is a demo image of that, and using the SQL library, we can also extract the images like the LBP features. This is one example of that. You can see ours does a quite better work than the SQL one, but of course we can change the tweak the feature parameters here and make improve this too. Now for the histogram of oriented gradients, first of all we resize it into 64 into 128 size. That 64 into 128, and that's convenient for HoG. Then we find out the vertical gradients. This function is also written from scratch. You can see that in the vertical gradient image, the features are mostly vertical, and in the here we have the one such function called horizontal gradient. Here the features are mostly horizontal. That's the difference between vertical and horizontal. And now we just add up both vertical and horizontal gradients, like to look at how the output image looks like. And now we use the write the actual HoG function. This is for the this part is, you can see, for to calculate the magnitude of gradient, and this part is for calculating the angle. Here we add the power of gx and gy and take a square root of that. Here we do the tan inverse of gy by gx for calculating the angle for each pixel. Now we have here is the magnitude of the each pixel of the image. You can see the difference that these parts which were quite significant in this simple addition are not significant here, and have just turned black. In the angle section, you can see the sharp lines have very different angles, so it has been given here. Now for the final histogram oriented image, this is the image. There are the different gradients with the angles plotted together. Now the next part will be explained by Vignesh.
Hello, this is Vighnesh and I will continue the video. Yeah, so now we'll talk about the convolutional layers. So, what does convolution mean? So, in convolution, what happens is that we have a kernel, which is essentially a matrix, a square matrix, um, or any other type of matrix, and it has some numbers in it, right? So, and you apply convolution on an image on with this matrix. So, what does it do is that it multiplies this matrix with a similar subsection of an image with a similar width and height, and then it adds the elements from the resulting matrix, and then it does this all over the entire image space. So after applying kernel, the new matrix we obtain is of the dimensions image height minus kernel height plus 1, and image width minus kernel width plus 1. So this is a function which implements this convolution function, and we can see we have done this for three kernels, one for detecting horizontal edges, one for vertical edges, and one another is a Gabor matrix. So when we ran the vertical edge matrix on this image, we can see this is the obtained image, and what has this done is that it has highlighted all the vertical edges in this image. So we can see, and if we compare this to horizontal edges, we can see that all the lines in this images are horizontal, like this chin line and this, all of these are horizontal compared to this, all these lines are more or less vertical or somewhat diagonal. So this is the result. And the Gabor matrix, if we contrast it to the original image, then it has like normalized to a certain extent the overall image. So like the contrast has been reduced. And if we add all of these pieces, we can say this is the obtained image. Now proceeding to the classification, we use three classifiers for each of these feature extraction techniques: SVM, KNN, and decision tree. So we found interesting results from all of these classifications. So yeah, this is like, and we also tried implementing PCA. So what happened was that when we applied PCA on our X10 and X we found that the, as you can see, this is the explained variance ratio for the first 10 components. And as you can see, it's only 25% for the highest one, then followed by 14%, then 6%, and it declines rapidly. So we did not think that implementing PCA for a few number of components would help like summarize the data to a certain extent. It would only cause the accuracy to reduce down while not changing much of the training time, because as you can see these percentages are very small. If we just add them up, we barely get 50%. So to reach a good variance ratio of, like, let's say 80% or 90%, we would have to take a lot of components. It would be like something like 200 or 500, and our number of components in this is 1840, like 57 into 30. So if we take that many components, it wouldn't drastically change the execution time, as well as it would give us uh, less accurate results. So which is why we tried, which is where we thought that we should using PC was not worth it. And now these are the results with the LBP features. So I'll see. So as you can see, we got an accuracy of 17%, which is pretty decent overall. And yeah, this is the confusion matrix. uh, we can see like the data for George Bush has very high accuracy, and this is because if you look at the data, like the data set, you find the most number of images were of George Bush. So maybe this is due to the fact that there were a very large number of images of George Bush, and that is why there is George Bush has much higher accuracy than other presidents. Yeah, so 70% accuracy, and these are the other metrics. For KNN, the accuracy was higher at 83%, and you can see it more or less forms a diagonal matrix, which is much better than this one. But the accuracy and other matrices metrics were lowest for the decision tree, and maybe the result reason for this could be that the decision tree is not able to form a well accurate decision boundary for multiple classes. These are 7 classes, and these are all images. So maybe the decision tree is not able to adapt well enough to this our feature space. So this could be at compared to different other classifiers like KNN and SVM, which are able to adapt well to the dataset more or less. You can see accuracy only is 45%, which is quite low. And now these are the results with HoG. So HoG gave us much better results overall. Like the accuracy rose to 76% for SVM, and you can see the matrix is kind of diagonal. And if we go on to the KNN, we can see uh, the accuracy has gone down a bit, but yeah, it's still a bit much more diagonal than this matrix. And for the decision tree, also it has gone down by 2%, which is not big, but yeah, we can see like it looks much better, well distributed than the this one, which is like quite a bit separated and distributed. So you can see like HoG all around the board has improved the accuracy and results for all three of our classifiers, and then we move on to CNN results. For CNN, we this is our model. So there are two convolutional layers, and both have only one kernel each. And these are the other parameters. You can see we are using a dropout of 0.5 to not like overfit the data. And like we have trained this for 50 epochs, and the model accuracy at the end was 88%. So what we did was created a function which took an image and outputted the activation of that image for our convolution layer. So like for this example image, this is the actual image, and this is the output image for the first convolutional uh, layer. So then we trained like we yeah, we did data for all this, and then this is the result for SA. You can see the accuracy is 75%, which is pretty solid. This is higher than the LBP one, and as you can see, yeah, the matrix also looks better than the LBP one. This quadrant looks like diagonal, except for a few outliers. And then if we go on to KNN, we can see that the accuracy has dropped down quite a bit. So the reason for this is not quite clear, but maybe this is because of the KNN is not maybe able to adapt to the decision boundary. for the images activation map produced by the CNN filters. So maybe if we try experimenting with different parameters of n neighbors, or try tinkering with the convolutional layer, so maybe we will find a much better accuracy. Yeah, and for decision tree, also the accuracy has gone down to the is equal as the accuracy for LBP and other parameters also. The matrix also does not look much better because it is distributed all around the place. So we can see like the best from this results, we can see that the best performing classification technique for these classifiers, feature extraction technique for these classifiers was HoG, and followed by like the accuracy for CNN extraction and UV extraction was more or less equal, and HoG outperformed all of them for feature extraction. So this was the our finding from this experiment.